So we're told that y equals this series here. Some constant multiplied to a variable being raised to the nth power. We're asked to find the power series expansion for x times y prime. So we don't know what y prime looks like, but what we can do is we can look at some of the terms of the series of y. So when n equals 0, then we have a sub 0 x to the 0. And then when n equals 1, then you've got some new constant, a sub 1 x to the first, plus a sub 2 x to the second, and then it keeps going like that, right? Actually, let's do a few more because we're going to need to look at the second derivative eventually. So we got a sub 3 x to the third. Okay. So you could differentiate term by term because when you evaluate a derivative of an expression, it kind of acts like the distributive property. You can find the derivative of each term separately. So this is just the derivative of a constant, right? Because x to the 0 is 0. So the derivative of a constant is 0. Here, this derivative is just a sub 1. And the 1 comes down, gets reduced by 1 when you evaluate that derivative. Here, the 2 comes down. Here the 3 comes down, and keeps going. And we need to also know something about the second derivative, so while we're here, let's do that. Take a derivative of this term, that's just 0. The derivative of this term, that's 2a sub 1. Derivative of this term, that's going to be 6a sub 3 x to the first. And then if we had another term here, that would be 4a sub 4 x to the third. So if you find a derivative of that, that would be 12a sub 4 x to the second, because the 3 would come down and multiply. And I think that's enough to detect the patterns. So we're supposed to create a power series for this, which just means you're multiplying x to everything. So x times y prime. This is what our y prime is. This is at least part of what y prime is, and it's enough so that we can find a pattern by looking at this. And so you can distribute that x. So we're trying to make a power series, so we want to represent what's happening with this series in terms of n. Oh, that's x to the fourth now because everything's getting multiplied by x. And just a reminder, we're evaluating x, y prime right now because we're distributing x to what we found y prime to be. Let's see, so n starts at 1 on the series notation they're trying to get us to do. And then it goes to infinity. So this is a sub n, right? Because when n equals 1, then we got this. When n equals 2, oops, I copied something down wrong here. That should have been a 2 here. Now that probably makes more sense. So when n equals 2, then we got a sub 2, just like we're supposed to. But we also have these coefficients out front. There's 2, there's a 3, there's a 4. It keeps increasing. So we have to actually multiply the a sub n by n. Because n is counting up. 1, 2, 3, 4, 5. The coefficients are counting up. The coefficients of a sub 1 are counting up. 1, 2, 3, 4, 5. So if you plug in some numbers and test it out, it's matching what we're doing so far up here. Except for the last part, we need an x, and the powers of x increase with n. So that's the full series, okay? Because if n equals 1, plug it in, you get a sub 1 x to the first, just like we're supposed to. When n equals 2, you get 2 a sub 2 x to the second, just like we're supposed to. When you plug in n equals 3, you get 3 a sub 3 x to the third, like we're supposed to. So we detected a pattern by just looking at not the whole series, but a few of the terms in the series. So I can do the same thing for this one down here. If you want to try it on your own, you'll want to pause the video at this point. But this is just x squared times second derivative. So that's every term is going to get multiplied by x squared. So that's 2a sub 1 x squared plus 6a sub No, I wrote this down wrong. Man, that's a bad copying error because I could have messed everything up. Okay, so that was a sub 2, this the third coefficient of the original series. So every term is getting multiplied by x squared. So that's what that is. This is 6a sub 3 x to the third. Then we got 12a sub 4 x to the fourth. And it keeps going. So the powers of x keep increasing. So here, with our series notation, they want us to do it from n equals 1 to infinity. X it starts on 2, so we can't just put an n up here, right? Because then the first term of the series would have x to the first power. So we got to increase that by 1. And now the powers of x match what's going on with the series. We got x to the second, x to the third, x to the fourth. Same type of thing with the a's, with the original coefficients. It's a sub 2, a sub 3. So we got to start on a n plus 1. That way, when we plug in the first term, 1 plus 1 makes 2, just like it's supposed to. Now these coefficients out front are a little bit trickier. So this is a pattern that comes up quite a bit. One thing you can do is you could start writing out those numbers, trying to look for the pattern. It'd be nice if we had another one, but you could factor out a 2 from all those. And this pattern goes up by starts on 1, goes up by 2, goes up by 3, goes up by 4. That pattern is modeled by n times n. Oh, actually, I'm forgetting here. Is it n minus 1? Let's try. If you plug in 1, you get out 0. So it's got to have to be plus. Oh, no, it just needs this 2 gone. Okay. So the pattern trying to match these numbers up here, or these numbers up here, whichever one you want to look at, is n times n plus 1. Because if you plug in 1 in for n, 1 times 2 makes 2. If you plug in 2 in for n, 2 times 3 makes 6. If you plug in 3 in for n, then 3 times 4 makes 12. So we need that out front here. So to finish this out, all that stuff is right, I just need more room. And it takes a long time to erase on this thing. We need n times n plus 1 times a sub n plus 1 times x to the n plus 1 power. And again, you can test out these terms. You can plug in n equals 1, and it's matching the pattern that we found from the second derivative times x squared. Plug in n equals 2, matches what's happening here. So after I'm done videos, I go check to make sure my answer works out in WebAssign. This is WebAssign's version of the answer. It works, but it's equivalent to what we just wrote. Because if you plug in n equals 1, this is 1 minus 1 makes 0 times 1 a to the 1 x to the first. And at first you're like, well, there's not supposed to be an a sub 1 here, but everything's getting multiplied by 0, so this term cancels out. And then if you plug in n equals 2, that's starting to match what we were doing, right? Because then when you simplify this, you get 2a sub 2 x squared. So this is the same thing as this. WebAssign just didn't specify to us that we need to start at a sub n. So these are both equivalent, and so if it was like a free response on a math test, both of these would be acceptable answers. But just so you know, when you type it in WebAssign, I guess we got to type it in with their version of the answer. For the final exam in this course, there's not going to be a question that the multiple choice would only have this or this. So you won't have to worry about this type of issue. It's just an issue with WebAssign. So when you type in your answer, you're going to want this one in WebAssign.